Yeah, it's a great pleasure to have John Etnyre here in our symplectic Zoominar. He'll be telling us about symplectic embeddings and small symplectic caps. Take it away, John.
All right, great. Well, thanks, Bulent, and thanks to the organizers. I appreciate the opportunity to speak here, and I appreciate everybody from all sorts of different time zones getting up early, staying up late, and so on. So hopefully you'll enjoy the talk. So as Bulent said, I'm going to be talking about symplectic embeddings and small symplectic caps. So just that is the main goal in the talk today, is talk about how do you kind of in explicit ways build symplectic manifolds. In particular, symplectic four manifolds is what I'm going to mainly focus on. I'm actually working on trying to do a few of these things in higher dimensions, but at the moment we're going to stick with four manifolds. So before I get into the details of the symplectic problem and what we can say symplectically, I'd like to just discuss what happens in the topological or smooth setting. So, studying embeddings is, of course, a fundamental problem that, people have studied for, decades, if not centuries, like, for instance, embeddings of S1 and S3. This is classical knot theory, which is, of course, much studied. And the general question of embedding, say, an M manifold in Euclidean space or even some other N manifold has also been much studied. And, of course, everybody's probably very familiar with the Whitney embedding theorem, which says that any, that's the nice thing about having the tablet here, is you can actually fix it in real time. There you go. That an M manifold embeds into M. And of course, it's also fairly well known that you in general cannot improve this. But in some cases you can. For instance, Hirsch and Wall, I think Hirsch did the orientable case and then Wall did the non-orientable case, proved that any three manifold can embed in R5. So they kind of do one better than the Whitney embedding theorem in this particular case. And by the way, a fun little corollary of one of the reasons that you might want to study embeddings is because when a three manifold embeds in R5, it turns out it always has the equivalent, right? R5 has no homology, and that tells you that any three manifold which represents three homology is the boundary of a four cycle, and it's not too hard to prove. Well, you can't quite make it an embedded an embedded four manifold, but it's not too hard to surger it to get a four manifold. So by studying embeddings, we actually learn that three manifolds always bound four manifolds. Of course, we know that for many other reasons, but again, this is just kind of a nice, little extra you get out of studying embedding type problems. Well, in general, you can't continue to improve. For instance, all three manifolds do not embed in R4, and in fact, Xiaomi proved that there is no fixed compact four manifold into which you can embed all three manifolds. So really, the best you're ever going to do if you're asking about all three manifolds is R5. So how do you see that all three manifolds can't embed in R4? Well, the first obstruction is, notice if you have a rational homology sphere, so that just means, of course, a three manifold that has the homology of S3. Then if it embeds in R4, then it bounds a rational homology ball. And we know that this isn't true for all three manifolds. So I'll kind of discuss, and explore a particular case of that. In this talk, we're really going to be focusing on lens spaces LPQ. And for us, the definition of the lens space LPQ is you just take the unknot in S3 and you do minus P over Q surgeon on it. So it's just the union of two solid tori glued together in a particular way. And it's known that not all lens spaces can bound rational homology balls. So that then tells you that not all lens spaces can be embedded in R4. So in particular, let me give you an example of a lens space that actually does pass the bounding a rational homology ball test. So it potentially could embed in R4. So it's actually very easy to build such a rational homology ball. So when I draw this represents attaching one handle to the four ball or four disc, and then this green curve is a knot, and I'm going to then attach a two handle to that knot with framing one. It's very easy to play around with this kind of surgery picture and see that this the boundary is L41. So L41 does bound a rational homology ball. So you might think, well, it passed the first obstruction to being embedded in Euclidean space. So does it actually embed in R4? Well, it turns out that no lens spaces for positive P embed in R4. So in particular, this lens space that does pass the rational homology ball test doesn't embed in R4. So the way you can see that LPQ doesn't embed in R4 is it's a fun little fact that if you do have a 3-manifold that embeds in R4, then the torsion part of H1, the first homology, is a sum of a group with a copy of itself for some finite abelian group. So actually, this is a really kind of a fun, whenever you're teaching algebraic topology, it's a great exercise to give people once you've got your Meyer-Vietoris and long exact sequence of a pair. But of course, no lens space. The fundamental group of a lens space is, of course, Z mod P, and Z mod P can't be written in that form. So in particular, L41 doesn't embed in R4, but you then ask, okay, fine, I failed on my first attempt to get an embedding. Can I embed it anywhere? And the answer is yes. So in fact, it's very easy. You just take this rational homology ball that you had. If I glue on another 2 handle with framing 0, and then you can fairly easily see that the upper boundary is the 3 sphere. So you just need to then attach a 4 handle, and I get a closed 4 manifold. A little bit of manipulation, you cancel this 2 handle with this 1 handle. This is the picture you have left, and that's, of course, well known to be CP2. So we can't do R4, but we can do kind of the next best thing. CP2 kind of has the smallest possible homology of a compact manifold that isn't S4, and we can actually embed our lens space there. Great. So we've solved the problem for this one example. So what can we say in general? Well, the first thing to observe is, okay, our lens spaces, none of them can embed in R4, but you might ask, okay, which ones of them embed in CP2? Well, it turns out that if you can't embed it, then either the lens space or the lens space with the reversed orientation must bound a rational homology ball. And so why is that? Well, it's fairly easy. Of course, your lens space is going to have to be separating in CP2, and if it's separating, it divides it into 2 pieces. And well, the homology of CP2 is just Z, and so one side is going to have a Z, and the other half is going to have to be just torsion. So again, we have the same obstruction to embedding in CP2 that we had in R4. It turns out that Liska, in a really beautiful paper in 2007, was actually able to tell you exactly which LPQs bounded rational homology balls. The criterion is actually kind of long and it's not relevant for us, so I'm not going to go into it. But he does have a very precise criterion that tells you when your lens space bounds a rational homology ball. And if it doesn't, then of course it can't embed in CP2. So in particular, he can obstruct L31, L51, lots and lots of other ones. Won't bound rational homology balls, so they will not embed in CP2. Okay, great. So that was just kind of a review of what we know about embeddings of a particular class of rational homology balls, namely lens spaces, into R4 and CP2. Now we want to consider a similar sort of problem, but in the symplectic category. So we're going to ask, well, when can we embed these lens spaces, or in particular, maybe some rational homology balls in CP2? So let's kind of build up to that. So when we're trying to do symplectic geometry, of course, we just don't want to look at any embedding. We want to actually have the symplectic structure come into play. And the way you naturally do that is, if you're given any manifold with a contact structure, and you have a symplectic manifold with a 4-manifold with a symplectic structure, then we say the embedding is we can embed M into X as a hypersurface of contact type if, well, first of all, it needs to be embedded, but you need an embedding such that you have a vector field. And so you can read the slide here, but I'll just look in the picture. You need to have a vector field that's transverse to the image of your embedding, and that vector field needs to expand the symplectic form. And so it's going to divide X into 2 pieces. We're going to have one piece here where your manifold looks like the convex boundary of X1, and then it's going to be the concave boundary of X2. So this is the setup the sort of problem you want to study when you're talking about embedding contact manifolds and symplectic manifolds. So there's a nice little fact that whenever you have a lens space, then this part where it's the convex boundary of it, turns out it has to be negative definite. And we just said that when you have a lens space embedded in CP2, one side is a rational homology sphere and the other side has to be positive definite. So that means that actually if you can embed your lens space, then this x1 side, this x1 side over here, the side with a convex boundary, must actually be a rational homology ball. So now our problem is to study, or at least the start of our problem is to study which kind of lens spaces here can bound rational homology balls. Okay. So we'll get back to that problem in a second, but let me first start to think. I'm trying to build these rational homology balls and build these embeddings. So what are the tools and techniques I have to do that? Well, some fairly well-known constructions of symplectic, say, form manifolds is you can look for complex manifolds in complex projective space. You can use symplectic reduction. You can use Leschetz pencils. I'm sure lots of other people have their favorite constructions. These are the ones that I'm kind of most familiar with. But the construction I want to talk about today is I want to try to glue together two symplectic manifolds, basically a symplectic cap and a symplectic filling of the same contact structure. So let me just recall, I think everybody's familiar, right? But a symplectic filling, and I'm going to always be interested in strong symplectic fillings, is simply a symplectic form manifold X whose boundary is your manifold M, and you have a expanding vector field near the boundary. And if you contract that vector field into symplectic form, this gives you a contact form for your contact structure on the boundary. So this is a strong symplectic filling. So that's one of the pieces we're interested in. But the other piece is a symplectic cap, which is, of course, just the opposite. A cap is exactly the same thing, except now your vector field is going to point in to the manifold. And again, would say that maybe has concave boundary. So there's lots and lots of constructions of symplectic fillings. This has been studied quite a bit. We know an awful lot about this. I'll say more about it in the case of lens spaces shortly, but we know a ton about this. The problem is constructing the symplectic caps. Well, it's not so much of a problem because back in 2002, Kohanda and I were able to show that all contact 3 manifolds do have caps. So in some sense, great. We have our fillings, we have our caps, so we should be able to build our closed symplectic manifolds. Well, it turns out this theorem abstractly is very nice, but in practice, if you're trying to build small symplectic manifolds, it's super unhelpful because this construction that we gave to prove this theorem always produces caps with very, very large topology, huge topology. So really large homology, for instance. So we're not going to be able to use, this strategy here with kind of just our standard caps we get from here and fillings we get maybe from, I don't know, Stein constructions or something. So we have to maybe try to come up with some other idea to try to get small symplectic manifolds if we're going to try to build, say CP2 or maybe even exotic CP2s or something. Okay, great. So now I'll just kind of rephrase what we're going to try to do in the rest of the talk. I've already said we'd like to build symplectic caps, but in particular, I want to build small symplectic caps. The second thing I'd like to do is I'd like to understand symplectic structures on form manifolds using handle attachments. So again, different people have different perspectives, but I come from a topological background, and I really like my form manifolds to have really explicit handlebody descriptions. And of course, we do know from Eliashberg and Weinstein that we can build Stein and Weinstein manifolds by attaching 0, 1, and 2 handles, where the 2 handles, of course, have some restrictions based on the Thurston-Bennekin about how you can attach them. So great, we understand how to attach 0, 1, and 2 handles in a symplectic manner, but we do not have a very good explicit construction for attaching 3 and 4 handles. David Gay has a really nice construction where he can tell you how to attach kind of round 2 handles, but which those include a 3 handle. But the problem with those is they require manifold to have torsion, which means they can't have a symplectic filling. So again, it's not going to be a useful construction if we're trying to build small closed manifolds. So, so these are 2 of the main goals. A third main goal is I'd like to have a very kind of explicit handle-body understanding of the following really interesting result. So let me tell you about an interesting result about lens space embeddings. To do that, we have to do a little bit of background. So a Markov triple is just 3 integers satisfying this equation, p1 squared plus p2 squared plus p3 squared equals 3 times P1, P2, P3. So it seems like a very strange kind of equation that you might want to study. But this has been much studied in number theory, and it shows up all over in lots of surprising places geometrically. For instance, what are some examples of these Markov triples? Well, clearly 1, 1, 1 satisfies that. 1 plus 1 plus 1 equals 3. And it's not too hard to check that 1, 1, 2 does, 1, 2, 3, 5 does. And notice if you have a Markov triple, you can easily prove that if you then replace P3 with 3 times P1 times P3 minus P2, you get another Markov triple. So basically, you can start with 1, 1, 1, and you can just kind of keep it. You can build this tree, and eventually it just becomes a binary tree, and you'll wind up getting all possible Markov triples. Okay, great. So why are we interested in Markov triples? Well, before I tell you why, let me give you one other piece that we need for the statement of the theorem I'm interested in. So I'm going to construct a rational homology ball BPQ as follows. I'm going to start by attaching a one handle to the 4 ball. And of course, we can do that in a symplectic way and get a Stein manifold or Weinstein manifold. And then I'm going to attach a 2 handle to this Legendrian knot. So this Legendrian knot goes P times over the handle, and there's going to be kind of Q of these zigzags in the handle. And just like I said before, if you look at this picture, this is close to what we had before when we constructed a rational homology ball whose boundary was L41. Well, in general, you can fairly easily prove that this thing is actually L p squared PQ minus 1. So basically, we've just constructed a whole bunch of rational homology balls with boundary lens spaces. Okay, so what's the interesting result I want to try to understand today? So Viana proved that given any Markov triple, you can find QIs such that these 3 rational homology balls embed in CP2 symplectically embed in CP2, and they're disjoint. So in particular, he's telling us you can find a triple of lens spaces that you can embed in CP2 as hypersurfaces of contact type. And really, quite amazingly, a year later, Evans and Smith were actually able to show that these are the only homology balls that embed in CP2. And I mean only in the sense that you don't even have to do a triple. If you give me one of these BPQs, if P is not part of a Markov triple and Q did not come from his theorem, even that one rational homology ball does not embed in CP2. And therefore, the associated lens space also doesn't embed, because remember, if it embedded, it would have to bound a rational homology ball. So so it's really kind of amazing that we just have a complete necessary and sufficient condition for these embeddings, symplectic embeddings in CP2. Okay, great. So what about other potential lens spaces or rational homology balls that might embed that aren't coming from this BPQ construction? Oh, sorry, maybe our slides are out of order. Anyway, I think this is fine. So how did Viana prove this theorem? So he proved it using almost torque geometry, and I'll just say a couple of words about that at the end of the talk. So the kind of the buzzwords that get used are nodal slides and transfer the cuts to kind of give different almost torque pictures of CP2, and that's what gets these different embeddings of rational homology balls. Okay, great. So so I'd like to just kind of review what do we know about, as I was said on the last page, what do we know about contact structures on lens spaces that bound rational homology balls? Well, Liska in 2008 completely classified which universally tight contact structures on LPQ bounded rational homology balls. So we have a complete list, and that list is essentially the ones that come from this. That's it. So this result of Viana is really telling you about all possible lens spaces in rational homology balls that embed in CP2, because Liska said that was all you had. But that's only for universally tight contact structures. Of course, we know that most lens spaces have even more virtually over-twisted contact structures. So, contact structures that when you pull back to a cover become over-twisted. And very recently, using some work of Christian and Menke, Agniva Roy and I, as well as independently Austin Christian and Lee, proved that basically no virtually over-twisted contact structure bound rational homology balls. So between these two things, we know all possible contact structures on lens spaces that bound rational homology balls. Great. So lots of lens spaces don't. So for instance, lots of lens spaces don't embed as hypersurface contact type in CP2. For instance, this L95 is the boundary of B32, and 3 is not a Markov part of a Markov triple. So even though it does bound a rational homology ball, so it satisfies the obstruction that we talked about earlier to embedding in CP2 just smoothly, it can't embed as a contact manifold. Just to give a little bit more context, it turns out that lots and lots of lens spaces will embed smoothly. In fact, Owens, after the Iano result, actually was able to construct lots and lots of examples. Basically, these rational homology balls, where these things are the Fibonacci numbers, actually embed in CP2 smoothly, but they don't symplectically embed. So just to, since I don't want you to have to work out those numbers, here's a particular example. L2514 bounds a rational homology ball, and it does topologically or smoothly embed in CP2, but it will not embed, since 25 is also not a Markov number, it will not embed as a hypersurface of contact type. So we're seeing a really nice distinction here between the symplectic and the smooth world. I should also mention, after Owens, actually Liska and Parma gave lots and lots more examples. They gave examples that included this family, but just lots and lots of other families using a technique called horizontal decompositions. And in fact, it's not something we're going to address today, but I'm actually very interested in this question. Can we actually characterize which lens space is embedded in CP2? I mean, Liska told us which ones bound rational homology balls, so we at least have a list of things to try. We have a ton of examples of embeddings. Can we prove that this is everything, or can we embed other ones? Yeah, don't know. But I think it's a really, really interesting question for future work. Okay, great. So now I can finally tell you the theorem that we're going to discuss the proof of today. So this is joint work. I guess I should have said at the beginning of the talk with Hyunki Min, Lisa Piccirillo, and Agniva Roy. So basically, suppose you have a Markov triple and you have these QIs, just as in Viana's result. By the way, Viana tells you exactly what these QIs are supposed to be. They're not random QIs. So what we're going to do is we're going to give an explicit handlebody construction of a symplectic cap for the union of these lens spaces. And that cap is going to have B2 equal to 1. So just the picture here is we're going to build this orange, cap for all these lens spaces. And then you can take these rational homology balls that were constructed a few pages earlier, and we glue them together. I'm going to call that manifold X, P1, P2, P3. And these things are homology balls. This thing has a second homology of rank 1. So it's really not very hard to show that these manifolds are simply connected. Their homology is Z, and therefore Friedman tells you that these symplectic manifolds that I just constructed are CP2. So when you first see this, you're like, great, these are really weird things. Maybe we've constructed an exotic CP2. Well, unfortunately, another thing we proved is, well, they're actually all CP2. So the point is, this is a handlebody construction that gives you all of Viana's embeddings into CP2. I should also mention that Liska and Parma also proved that these rational homology balls embedded in CP2 smoothly. They didn't consider the symplectic structures. Okay, so this is kind of the main results that we're after. All right. So how are we going to do this? How are we going to try to construct these explicit handlebody pictures? So the proof has basically 3 main ingredients.
I'm confused. And what about symplectic structure on the CP2? It's non-standard, or?
Oh, no. So once we know that it's smoothly CP2, then there's a result of Taubes that basically tells you that there's a unique symplectic structure, up to deformation or whatever on CP2. So the symplectic structure comes for free, well, free after Taubes does some hard work for us. So the symplectic structure is the same too. Yes. Thanks.
So
I should have
constructed embedding of these caps into standard CP2.
Exactly. Yes, that's right. That's correct.
Thank you very much.
Great. Okay, great. So what do we need to use here? So the first thing we're going to do is I'm going to remind you of a construction of David Gay. This was actually in his thesis from from Berkeley back in, I don't know, 2000 or give or take a little bit. But I don't think it's actually been used a lot. So we're going to give a really nice application of this construction. So I'll tell you about that shortly. Then you actually have to understand non-loose torus knots in over-twisted contact structures. So recently, with Min and Mukherjee, we were able to classify those in S3, and then we slightly upgrade that to some non-loose torus knots in lens spaces, and that's the second ingredient. And then finally, we have to do a lot of handle calculus. I'll try to sweep most of that under the rug, but there's, that was some of the hardest parts along the way. Well, once we'd already done this part. Okay, so let's try to get started and discuss these two main results that we're going to need. So to state Gabe's result, I need to remind you what an open book is, and in particular, what I'm reminding you is we actually need to talk about rational open books, so a slight generalization of open books. So given a three manifold, if you have a pair, B, which is going to be just some link in the manifold M, and pi is a projection from the complement of the link to S1, if that's a fibration such that the pre-image of, well, such that if you take any one of the fibers and take its closure, that each boundary component of that fiber is going to wrap around some component of B. So I guess I should say this thing, yeah, so, oh, sorry, I was going to say, I thought I was going to emphasize something else. But basically, if this thing is embedded, so you're not wrapping around, you just wrap one time around each boundary component, then you drop the word rational and you just call it an open book. So let me just kind of give an indication of what I mean by that. So near one of the binding components, you can have something that looks like this, right? And so this is just what you see for a standard open book. A single page comes in just like that. But here we got an example where the page is actually going to kind of come down, run 3 times around one of the binding components. So this could not happen in an open book, but is okay in a rational open book. And just to have something to think about, if you look at the hot link sitting in S3, its complement is just T2 cross interval. Well, it turns out it's really easy to fiber T2 cross interval by annuli. Just take any embedded curve in T2 and cross the interval, and that's going to foliate a T2 cross interval by annuli of various slopes. And you can do that as long as the slope isn't 0 or infinity, the slope of the curve. And why is that? Let's think about this. So here's an example where I took slope 0. And if you think about putting this link back in, this boundary is going to come in as a meridian to this. And you can't come in as a meridian. You have to wrap around the knot. So this is not allowed. But here's an example where it's going to wrap 2 times around one component and 1 time around the other component. So that's an example of a rational open book. If I just took the slope -1 thing here, that would be the standard open book that, coming from, like, say, the Milnor fibration. Okay, so these are rational open books. Why do we care about rational open books? First of all, we have this notion of a contact structure being supported by an open book, and that simply just means that the binding, this B link, is positively transverse to C, and you can pick a contact form for the contact structure that's positive on the pages. Well, I guess I should say the interior of the pages. So the interior of the pages are symplectic manifold given by D of the symplectic form. So back in 1975, Thurston and Winkelkemper, of course, proved that every open book supports a contact structure. A little bit later, Ken Baker, Jerry Van Horn Morris, and I were able to prove the same thing for rational open books. And I should actually mention this uniqueness part was not due to Thurston and Winkelkemper. That really, maybe I should even put it here. Just so this is actually Giroux. Okay. So open books are related to contact structures. And just a little bit more terminology, which people are, again, probably familiar with. Since the complement of the binding fibers over S1, we can always write it as the mapping torus of some diffeomorphism of the surface. So you just, you take your surface, which is a preimage of one of the points. There's going to be some diffeomorphism here. And the one thing I should mention, that unlike the case of honest open books, this diffeomorphism doesn't have to fix the boundary. It can take one boundary component to another boundary component. It can rotate the boundary. But we can still talk about these things. And of course, we're going to call phi the monodromy, and it completely determines our open book. Great. So what can we do with this? Well, here's the theorem of Gay that I would like to tell everybody. But like I said, I think it's an amazing theorem, and it's really exciting that we have a nice application of it now. So David Gay proved this for honest open books. And in our paper with Min, Piccirillo, and Roy, we generalized it to the case of rational open books. It was really just kind of epsilon addition to what David had already done. So the theorem says if you have an open book for some contact manifold, we're going to denote the boundary, the binding, B1 through BK. And for each binding component, I'm going to choose some integer. And that integer, well, think of those integers as framings, and the framings need to be larger than the framing coming from the page of the open book. As long as that's the case, then you can take this manifold W, which is just, you take a bit of the symplectization of M, and then I'm going to attach two handles to the upper boundary along the binding with framing given by these Ni. And what Dave Gabe proved was that this manifold W has a symplectic structure where both boundary components are concave, right? We're used to, when we're building symplectic cobordism, start with a piece of the symplectization, attach, say, Weinstein 1 and 2 handles, and then you have a symplectic manifold with a concave boundary at the bottom and a convex at the top. Well, here, both boundaries are concave, and this is the key that's going to make everything work for us. And moreover, we can actually say what exactly the upper boundary is. Of course, the lower boundary, you just started with, M cross 0, so it's just your original contact manifold. And the upper boundary is going to be topologically the result of minus Ni surgery on the mirror of Bi in M with the opposite orientation. And the contact structure we're surgering is actually the contact structure supported by the mirrored open book. So that's the statement. We'll see this in practice in a little bit later, but let's kind of explore what you might try to do with this now. So notice if the MC is fillable, then you can glue that filling to W, and you now have a cap for, well, this upper boundary that you constructed in the theorem. So for instance, if you started from S3 and you perform this construction, and you say had an open book, a rational open book with one boundary component, then you could construct a cap with very small B2. So this is a construction where you could try to construct, well, in fact, I can construct countless caps for contact manifolds with very small B2. There's one problem with this whole story. It's the monodromy, right? So if you look at the monodromy of this thing, right? So remember, our upper boundary is going to be gotten from this thing by some surgery. So what is this thing? Well, the monodromy for this is the inverse of the monodromy for the original contact structure. So the problem for that is if you started out with the original contact structure being tight, that means your monodromy is right veering. That means this monodromy is left veering, which means this contact structure that you got here in the theorem is not tight. It's going to be an over-twisted contact structure. So that means when I do surgery, you expect to probably still have an over-twisted contact structure. Right? So that's a problem, right? Because now I've constructed caps, but I constructed caps for over-twisted things, and those are always really easy to construct. And well, that's not so interesting because you can't glue those to a concave piece to get a closed manifold. So we have to try to understand how to do surgery on knots and over-twisted things and get things that are fillable if we want to try to apply this theorem to build closed symplectic manifolds. Okay. So recall, one of the rational homology balls we want to embed is just this BPQ, and here's the picture for it again. So the boundary is a Slin space, as we've already said. The contact structure is the universally tight contact structure. So I want to talk about applying Gay's theorem here. So to do so, I just want to remind you, how can I think about this Lin space? I can think about the Lin space by taking this green thing, which is just T2 cross interval. So this right here is T2. Here's the interval direction. And if you collapse the curves of slope minus P squared over PQ minus 1 on the back face, and you collapse the curves of slope 0 on the front face, this is the Lin space. Okay. The reason I'm giving you this description is we can take this torus right in the middle here, this T2 right in the middle, so say T2 cross 1/2, and I can take an RS slope curve on it. So that's what I mean by a torus knot in a Lin space. And suppose I attach a 2 handle to a bit of the symplectization of this Lin space along this curve gamma in the upper boundary. with the framing coming from the torus that it sits on, right? So the torus frames the knot. It tells you how to attach the handle. So I'm going to call that manifold W. Okay. Call that manifold W. So the boundary of W, well, the lower boundary is your lens space. The upper boundary is something M called M. And right now we want to figure out what is M. What is M? Well, notice M is the result of, well, that framing Dane surgery on gamma. So how do you get that? Well, here's the lens space. I've just kind of, sorry, yeah, here's the lens space. I've just kind of cut it up. I've cut it along that torus T1/2, and I've removed the neighborhood of the curve I'm surging on. Sorry, I couldn't draw this thing in perspective, so I just made a simpler version. But you're supposed to think about this white thing as the neighborhood of gamma that I'm removing. And so I've got my lens space. When you do surgery, you remove that solid torus. I'm going to glue in your surgery torus such that the meridional discs go to whatever the framing was. So that means this meridional disc is going to glue to that bound, right? This red right here, that's an annulus in the complement of the knot. I'm going to glue this disc to one of those boundary components and this disc to the other boundary component. So this gives me an S2 inside of M. So M is going to be the connected sum of two things. And what are those two things? Well, look at what's on this side. Well, this is a solid torus, and I'm going to glue basically a three-dimensional two-handle to it. That's going to give me a lens space minus a ball. Similarly, this side with this is going to be a lens space minus a ball. So in particular, we get M as a connected sum of two other manifolds. It's fairly easy to see that one of those is actually L RS, where RS, remember, was the slope that we took here. And the other one is some other lens space LMN. But if you do a little bit of work, actually a lot of work, a little bit of numerology on the Markov triples, you can actually arrange that that if you started with one of the Markov triples, say P3, these other two things can be, and you chose the RS correctly, one of them is going to be the thing you get from the other Markov triple, and the third is going to be from the third part of the Markov triple. So at least topologically, we're getting the right things here. And of course, we can add one handle. So if you take the rational homology balls that these things bound, and you attach a one handle, you now have the upper boundary is the connected sum, and you can glue W to it. And I now have a symplectic cap for this L, P3 squared, comma, P3 Q3 minus 1. So we've actually built a cap. But that's if we can glue these things on symplectically. So that's our question. So topologically, we can certainly build this manifold, but can we do it symplectically? So of course, clearly all of this is a symplectic construction. So the real question is, what happens to W? Can I make W symplectic? And moreover, can I make it symplectic so that I can actually glue it to the connected sum of the universally tight contact structures on the boundaries of these things? So that's our task for the rest of the talk. Okay, well, for W, right, the first bit is fine because you're just using the symplectization of the contact structure. So now the knot gamma is just going to be, as I said, it has to be this this torus knot on the T2 comma 1/2 in the lens space. And it's fairly easy to check that any positive torus knot, which this is a positive torus knot, actually supports the universally tight contact structure. So this gamma is the binding of a rational open book for that, that contact structure, which is the one that we're working with here already. So we can apply Dave Gay's theorem to this and get a symplectic manifold W. So basically this, this can be made to be symplectic. So now the real question is, what happens to the lower boundary? Is that, can I actually, does it have the right contact structure? Right, so the upper boundary is great, but is the upper boundary the right contact structure? So remember that contact structure is obtained from this contact structure on the lens space, and we know that contact structure is over-twisted, so we have to do surgery on this over-twisted thing to see what we get. So what can we say about that? That brings us to our second main ingredient, non-loose torus knots. But maybe before I dive into that, just quickly pause, or any questions about the general strategy of the construction of W. So again, just going back here, what we've got left to do is we've got to prove that this symplectic W that we've constructed has upper boundary with the right contact structure. In other words, the connected sum of the university contact structures on the other lens spaces. That's what this first part of the construction is saying. We now have to identify that contact structure. Okay. Well, this brings us to non-loose torus knots in lens spaces. So last year, again, Min, Mukherjee, and I managed to classify all Legendrian transverse Legendrians in overtwisted contact structures on S3. So we need to generalize this to at least part of that to some lens spaces. But just for the discussion here, to keep matters simple, let's just stick with S3 as I describe things to you. But again, the same thing works in a more general lens space. So, in particular, the Legendre knots we're interested in, or transverse knots, are what are called non-loose. And a non-loose knot just means that its complement is going to be tight in. So we're in an overtwisted structure, but you take the complement of the neighborhood of the knot, it's tight. So, so we need to study these things. We're going to describe curves on the torus in terms of elements of the extended rationals. Right, so just you pick a basis for T2. When I have a rational number, that's going to describe some closed curve on it. So for instance, this is the curve of slope 2. And to keep track of curves, we're going to use the Fairy graph. I don't want to spend a long time discussing this. Hopefully most people have seen this before, but I'll just briefly say, if you take the unit hyperbolic disk in R2, so this thing with hyperbolic metric, you label this point 0 and this point infinity and put in a hyperbolic geodesic. Now, in between any two points that you've labeled, like this point, you just add the numerators and the denominators of the point that it's halfway between. And so this will be 1 over 1, and then put in geodesics, and you just kind of keep doing that. So this is 1 over 1, 0 over 1. If I add those together, I get 1 over 2, and then hyperbolic, and you just keep going. So all the rational numbers are labeled here. And one of the key features about this that's useful is basically a lot of the classifications of contact structures in dimension 3 are phrased in terms of the Fairy graph. But you should interpret anything on here, like for instance 2, that corresponds to that slope. And one interesting fact is if you have two curves, two rational numbers describing curves, if there's an edge in the Fairy graph, it turns out they intersect exactly once. That's a useful fact as well. So let me not say too much more about the Fairy graph, but we will see it kind of appearing in a few statements later on. Okay, great. So I want to think of a solid torus, just like to describe the lens space, I started with T2 cross interval and collapse things, boundary components. Now for the solid torus, I'm just going to think of T2 cross interval. I'm only going to collapse curves on T2 cross 0. And on the other thing, I'm going to just specify some curves of a given slope. This is called a dividing slope. This has to do with convex surface theory. We're not going to get into details of convex surface theory, but the point is this is just a T2 boundary of a solid torus, and we've specified some curves on the boundary by some particular slope. So what's the important point here? Well, Zhu and Honda classified tight contact structures on the solid tori, and the classification is as follows. Well, this is a corollary. It's not exactly how they stated the classification, but this is how we want to think about it. So given a torus like this, then the tight contact structures with this dividing slope S are given by taking a minimal path in the Fairy graph from R clockwise to S, and then decorating the edges except the first one with a plus minus 1. Okay. And you can do the same thing where you collapse the curves on T1, T cross 1, and had your dividing curves on T cross 0. So actually, sorry, let me just go back. So for instance, if this 2 was your dividing slope, I don't know, your original slope was say 0, then you would take a minimal path in the Fairy graph. You wouldn't put a sign on this one, but I put a sign there. So that would basically say there's two contact structures, on the solid torus with meridian 0 and dividing slope 2. So that's what this theorem says. Okay. So for S3, how am I thinking of S3? Once again, I'm going to take a T2 cross interval, and I'm going to collapse the curves of slope 0 on the back face and infinity on the front face. And that is S3. Now I'm going to take a T2 that's in the center, and it cuts S3 into two solid tori. I'm going to call it V1 and V2. And now for each V1 and V2, I can look at the tight contact structures on it. So for instance, for V1, maybe you're going from infinity out to some, P over Q. So there's no sign here, and I've got signs there and there. And for the other solid torus, I'm going from 0 to the slope of the dividing curves. And again, I have signs here, but no sign there. So basically what I've done here is by these two different paths in the fairy graph, I get two different tight contact structures on V1 and V2. And when I glue them together, I'm going to get some contact structure on S3. The thing is, if you mix signs at all, that contact structure is usually going to be over twisted. But one thing that Min, Mukherjee, and I proved was that if you take any non-loose PQ torus knot, actually, there's more hypotheses here with the Thurston-Benneken less than or equal to PQ. We can understand the other ones too, but for the statement of this theorem to be true, you need to assume TB is less than or equal to PQ. Then it sits on one of these tori that I just described here that you get by gluing a contact structure on V1 and V2 coming from those two paths. So let's see. Got a little over 10 minutes. Great. Okay. So I just wanted to say, before we kind of go back to our construction, I just want to take a little pause and say what we know about non-loose PQ torus knots. First of all, I should mention Gygas and Anaron and independently Matovic have classified some PQ torus knots for certain PQ. For instance, Matkovic, it was for all PQ where P times Q is negative, and the Thurston-Benneken invariant was less than PQ, less than or equal to PQ. For Gygas and Anaron, they did a few positive and a few negative cases for very specific TB and Rs. But in the paper with Min and Mukherjee, we gave a complete classification for all P and Q and all TB, and we showed how everything relates. So I just want to kind of give you a little idea of how that works. So if we plot the rotation numbers in the Thurston-Benneken invariants of these non-loose representatives, you can see pictures like the following. So if PQ is positive, you can actually see in some over-twisted contact structures this infinite X. And so for each dot, there's an infinite number of different non-loose torus knots in that knot type. And when you stabilize the ones here, you get the ones there. And if I stabilize further, so this is one sort of picture you can have. You can also have a situation where you have this infinite X, except at each dot there's only one, except there where there's two. You can also see this kind of infinite V with all these kind of jagged mountain range things inside. And finally, you can see kind of an infinite X where you've got these kind of little wings kind of going off. So these are the only things you can see if you're classifying positive torus knots in S3. If you're classifying negative torus knots, then you can still get those first two X's, like this one and the one on the previous page. You can also get this X just like you saw on the previous page, except here you've actually got three different Legendrians. That new one that popped out of nowhere, when you stabilize in either direction, just becomes one of the ones you had before. And you can also have these infinite X's, but now the wings are on the outside instead of on the inside that we had with the positive torus knots. So basically, if you give me a PQ torus knot, I can give you an algorithm that will tell you exactly which of these pictures and in which contact structures you have them. Okay. Wait a minute, what's happened here? Okay. Let's get back to the problem at hand. So in this paper, we were able to show that if you took the negative PQ torus knot and you looked at this contact structure, so one of the tori has all pluses, the other one has all minuses, that this contact structure is actually the contact structure that's supported by the positive PQ torus knot, negative PQ torus knot. And if you do PQ surgery on this torus knot, then the upper boundary is actually the connected sum of the universally tight contact structures on the Lin spaces, right? Because remember, when we did this construction about doing this, by the way, I should say this PQ surgery is the framing coming from the knot, coming from the torus it sits on, right? So this is exactly what we did in the construction with the Gay's theorem. So we are getting exactly the right contact structures. So that means that we can actually glue everything together and get CP2, right? So, get C, P1, P2, P3, right? So remember, I guess I drew this picture differently. I started with this thing, and I attached this two handle, and the lower boundary was these two things, and then you glue in all the homology balls, And you now get this XP, P1, P2, P3. And this is actually a symplectic manifold, because we arranged the contact structures were actually the universally tight ones from our study of non-loose Legendrians there. But now the question is, we now know that this is a symplectic manifold. It does have it is homeomorphic to CP2, as we mentioned. But the question is it actually CP2? And well, we couldn't get that lucky that it wasn't. It is actually CP2. And there's two ways to prove it. One is you can just quote a theorem of Liska and Parma. By the way, this paper came out, I think, a couple of weeks before we actually published our paper, or put our paper on the archive. But we could just quote their result and prove this. But we actually proved it by doing a lot of handlebody calculus that was inspired by the almost torque pictures to inductively prove that these things are all CP2. So I'll just give you a little hint at how that goes. So first of all, here is a picture of, so this is just a smooth picture, right? You're not seeing the symplectic structure here. By the way, I should emphasize that, remember, we built an explicit symplectic structure using Stein handles. We attached a one handle here. That's also a Stein symplectic construction. So all of this is symplectic. All of this is symplectic. And with Dave Gay's theorem, all of this is symplectic too. So we have an explicit handle picture for all of the symplectic parts of this that all fit together to give you CP2. But if you don't worry about the symplectic geometry, you basically have this. So this is a one handle. I've attached three two handles, and then you attach a three handle and a four handle. And this is smoothly X, P1, P2, P3. And if you do this handle slide right here, this is going to change. So these things correspond to a Markov triple. When I do this slide, this is going to do one of those mutations that changes one Markov triple to a different Markov triple. And this move that we wrote here is inspired by the almost torque picture. So recall, CP2 has a torque picture like this. So right, you just take the triangle in R2, you cross the whole thing with T2, and on the boundaries here, you clap some circles based on the slope of the lines, and this is a well-known picture for CP2. So you can actually turn this torque picture into an almost torque picture by, let's say, one of these vertices. You can basically change the angle here and then add this kind of cut in kind of a singular fiber there. And then this is called an almost torque picture because basically you're not fibering everything by these tori. You've got some singular points. And it's very easy to see that if you just look at this part kind of cut off by that green curve, that is one of your rational homology balls. This is another, and this is another. And transfer the cut says take this cut and try to move it to the other side. So what you do is it turns out that this right here, because of some monodromy right here, this is just it looks like is the same as that, and this is the same as that. And by making this change, you actually change this BP1, P2 into BP1 prime, Q1 prime, where they're related by that kind of mutation thing I talked about earlier in the talk. So it turns out that since you can get from any Markov triple, you can get from 1, 1, 1 to any Markov triple by a sequence of these moves, and these moves are mirrored by more or less this slide. By the way, we actually have to do something a little bit more complicated than a single handle slide, but it's close. You can get down to the base case of X111, and when you draw X11, this picture becomes this picture, and it's very easy Kirby calculus to cancel that handle, pull one of these things off the other, cancel the three handle, and you're left with that picture. So you just very explicitly, inductively prove that all of these things are CP2. Great. So what's next for this construction? So it's actually really, really easy to construct embeddings of other lens spaces into CP2 blown up some number of times. I think it'd be interesting to understand, given a lens space, what's the optimal N where you can do this. I think this is a hard question, but I think it's an interesting question. We can also try to study embeddings into S2 cross S2 with the exact same construction of say, lens spaces. So I think these are all fairly interesting questions, but I think a much more interesting question, which is maybe quite a bit more speculative, is can you build other small caps that might lead to some exotic symplectic manifolds? So to do so, we know from the way, at least to try to use the same construction, it means we have to understand more non-loose knots in more contact structures so that we can do these surgeries. And it will be rare cases where the upper boundary of this gay construction is going to give you something that's symplectically fillable. But it happens sometimes. We saw the proof of concept just a few minutes ago. And so the question is, can we actually try to find other interesting non-loose knots, say in some overtwisted structure on S3, in some overtwisted structure on S3, such that when we do surgery, we actually get some symplectically fillable contact manifold. So if we can do that, those are actually potential candidates for exotic symplectic manifolds. So thank you very much.
Thank you. Thank you, John. Any questions for John?
May I ask a question? So from the viewpoint of packing problem, can you fill the full volume of CP2 with your caps, or there are some packing abstractions?
That's a good question. I actually, I think the question is, maybe it's better to think about it in terms of actually these almost toric pictures. And I think the answer there probably is that you probably can fill up all the volume with these 3 rational homology balls. So the construction that we're talking about here, it's nice because it's topological and people that work with handlebodies can maybe see certain things better, but it's not very sensitive to the specifics of the symplectic geometry. For instance, whenever we do gluing things together, we're having to rescale. So we're only kind of getting things conformally. We're not getting kind of the symplectic structure maybe on the nose. So I don't think this would probably be a great approach to really understanding, something about a packing problem with all this kind of constant rescaling. But I really haven't thought about it. But like I said, I do think from the almost toric pictures, I think you can probably expand. Again, I haven't thought about this, I'm not sure, but I think you can expand these balls out to, I don't know if you can kind of get the entire volume, but you could probably get as close to the entire volume as you like with the rational homology balls.
Thank you.
Can you explain again this almost toric picture? Like, how are the angles related to the Q and P?
Yes, sorry. So let's see here. So let me just look at, suppose you have just something like this. So what does this mean? So it turns out that what you want to do is when you cross this dotted line, so here I've got T2, and here I've got a T2. If I go along here, it's just a T2 cross interval. They're kind of canonically identified. But if I take this T2 and move it to this T2 by going across here, I apply a diffeomorphism of T2 along the way. So there's some explicit map, and that map is determined by the slope of these 2 curves, because you want this map to be such that the slope that gets collapsed here is the same as the slope that gets collapsed here. So if I look at, for instance, this thing, the contact structure here is going to be the same as the contact structure where, so I just collapse that line and I just have this and no monodromy. So basically this bit of the symplectic manifold and this bit of the symplectic manifold are the same thing. So it's because of this diffeomorphism you apply along the dotted line that allows that to happen. So what do we do at the end of this thing? How do we go from applying a monodromy to not applying a monodromy? Well, it turns out at this dot right here, we actually put in a 2 handle. And that 2 handle kind of undoes that monodromy, so you get back to no monodromy down here. So so this now very, very messy picture is, so we kind of understand, this bit here, right? This is just, what is it? S1 cross interval cross D2 with a standard symplectic structure on it. And then when we go over here, we attach a 2 handle. So that's what that picture represents. And so to get the right lens space here, basically the angle between these 2 edges has to be exactly right. So you have to, pick that angle correctly. And, similarly here and similarly here. And that's what I was indicating earlier, is that when we kind of move from this picture to this picture, let me kind of get rid of this, kind of this portion right here a little neighborhood of this portion and this portion are really the same, and this and this are kind of the same. But of course, if I'm going to make this part over here straight, then there has to be some angle to compensate over there so that everything fits together, right? And it turns out that if you just do the kind of numerology on all these P's and Q's and Markov triples, it turns out that the number you have to put over here when you made this thing straight is actually the mutation of the P1 Q1 into the P1 prime Q1 prime. And again, to actually see why that happens, you just have to sit down, work with the matrices to kind of make everything fit together. And yeah.
Okay, thanks.
Sure.
Any other questions?